You're working with Ray Weiss and with the real interferometer experts there, Peter Fritschel and Segura. But he really gained fame within LIGO when he moved to Louisiana and became the resident grad student in charge of the Livingston interferometer. And he was able to coax it to really good performance and surpassed Hanford, in fact, for our science runs. And I think this was a little bit of an eye-opener in a sense for Hanford, which had a reputation as the primary, LIGO site initially. It was the first to be installed and so on. So anyway, Rana, there were discussions about whether it was in the best interest of LIGO to let Rana graduate at all. But he did, in fact, finish his PhD this past year, this summer, and came here to Caltech, where we're happy to have him. So he's going to give us an update on how LIGO is continuing to improve through his efforts and maybe the efforts of some other people too.
Thanks. All right. So I'm mainly going to talk about. Oh, I have the stick. The sensitivity improvements that we've made in the last year, and I'm kind of going to gloss over what's been going on at the Livingston interferometer, because there it's been not so much working on the sensitivity, but more on the stability. So this is kind of what I've just said. I'll show a few pictures about what's been going on in Louisiana, and then there's 3 points that I want to hit about what we've done there in Washington to increase the sensitivity. So just as a refresher, it's a schematic picture of the LIGO interferometers. It's basically a Michelson interferometer. There's cavities in the arms to enhance the phase sensitivity of the interferometers. And then there's an extra mirror out front to resonantly build up the power, which is incident on the rest of the Michelson interferometer. And then the signal is read out through what's nominally the dark port or the antisymmetric port of the Michelson interferometer. This is a plot of the progression of the noise in the Livingston interferometer over 2.5 years. And with the latest curve here, the dark one being the sensitivity it had in the last science run at the end of last year. So in the beginning, we had some troubles even getting the interferometer to run for more than a few seconds at a time, and the noise was poorly understood. And as we went along, we started to understand the kind of things that make up this kind of noise curve, and I think the progress got faster and faster. And then we sort of hit this area around this time when progress became difficult, and again we stopped, or we didn't so well understand the noise sources we had anymore. And then, I'll tell you where we are relative to this now. So again, in the last science run, the black curve is what I just showed you as the best for the Livingston interferometer, and the red and the blue are for the 2 kilometer and 4 kilometer interferometer at Hanford. So you can see, at least in one spot there, the 4 kilometer interferometer was getting very close to this purple curve, which is our sensitivity goal. This is a histogram of the sensitivity of the interferometers over the course of the 2-month run. The thing that's plotted there on the x-axis is what we call the in-spiral range. This is as I show there, it's a sensitivity to the 1.4 solar mass neutron star in spiral with a signal to noise ratio of 8. And so that's the distance in megaparsecs averaged over polarization and also the antenna pattern of the interferometer, I think. So what you first notice is this big blue blotch there, that our most sensitive interferometer had a varying sensitivity by about a factor of 5. And so this is clearly not good. At some point we knew what was going on, and we had sort of a high sensitivity, and still, for a lot of the time we weren't there. And whereas the 2 others, which had sort of moderate sensitivity, they kind of stuck to where they were. And I'll talk about why this was. So in Louisiana, the work for the past yeah, full year now has been on upgrading the seismic isolation. I'll say why that is. This is a picture of the displacement noise of the ground at the two observatories. The noisier trace here, the red and the purple one, are for the Livingston interferometer, and the blue and the black one are for the Hanford interferometer. And here I'm listing a few of the sources which give us this excess. In this band here, from sort of 4 hertz down to half a hertz, it's mostly dominated by noise created by people and not the environment. So cars, trains, trucks, oil pipelines, and water well digging. This is a plot of the statistics of the ground noise over 600 days, and mainly, without looking at the numbers, the thing you should take away from this is that the Livingston interferometer, which is in green, is almost always noisier than the Hanford interferometer. Let's see. So the x-axis here, this is about 1 wavelength per second. So you can see almost all the time the ground velocity in Livingston is going at about 1/10 of a wavelength per second. The solution to this problem was to install active isolation outside of the chambers. The basic idea is to put inertial sensors on the payload which you're trying to isolate, and to also measure the ground noise, and then to apply feedback to hydraulic actuators which support the payload. This diagram here is showing what frequency bands we isolate over, and it's not labeled, but this corner is about 0.1 hertz. This crossover here is around 1 hertz, and then the end of this band is about 5 or 10 hertz. Here's another picture of the isolation system. Inside of the chamber is one of the cavity mirrors from the arm cavities, and the 4 blue piers that you see coming up. Well, you see 2 here, and there's 2 more behind the chamber. They support the optical table which supports the suspension. The blowout here shows you the hydraulic actuator and the springs which support the payload, and not so easy to see are the sensors which are located inside of here, which are used for the isolation. So this was installed first on just 1 arm cavity, and the results I'm showing you here are of the relative velocity between the 2 mirrors of the arm, the 2 mirrors which make up the cavity. The green curve is with the isolation off, and you can see that it's dominated by some peaks here at 1 and 2 hertz, and then sort of a broadband level from 0.1 to 1 hertz. With the isolation on, you get almost a factor of 10 reduction in the noisiest band, and then all the way down to 0.1 hertz. And there's some amplification below there. But the main thing to take away is that the RMS velocity, as seen by the arm, is reduced by almost a factor of 10 over the critical band. And this is a plot of sort of the worst of times seismically that the interferometer sees. I mentioned there's a train that goes by the observatory maybe 3 or 4 times a day. This is one time in the dead of night when the interferometer is running, and things are sort of going okay. This is the stored power in one of the arm cavities, and you can see it's kind of moving along nicely. The interferometer stops working for a while we tune it. We get it back going. Meanwhile, the train's coming through, and the ground velocity gets to be as high as 10 microns per second, which is about 30 or 100 times more than the 90th percentile level. And while it comes through, you can see there is some increase in fluctuations on a lot of these signals. The stored power in the arms, and also the power at the dark port. But the important thing is it keeps running throughout this entire time. And this was the first time we had the interferometer run through noisy conditions like that. So, without getting into all the details, basically all of the hardware has been installed for the isolation system, and the servos are being commissioned as fairly well. I think it's about 75% done. 75% done now. This is a little bit out of date. But the punchline sort of is that the interferometer can now work at all times, and the poor sort of 20 or 30% duty cycle that I showed in the first histogram should be much improved. So moving on to Washington, I want to say in a little bit more detail how the interferometer signal readout works. In the first picture, I just showed that the beam came into the interferometer, was resonantly built up, and then also stored in the arm cavities. There's a little bit more to it. The input beam is also modulated before it enters the interferometer. It's phase modulated at about 25 megahertz relative to the carrier frequency, which is about 300 terahertz. And then, so I've tried to show here that it produces three fields, and they don't really behave this. They don't really resonate in the same parts of the interferometer. And really, what you see is that the carrier light goes everywhere, resonates in the arms, also in this cavity here. But the sidebands there only resonate in the power recycling cavity, or the small Michelson area. This is a more complicated plot, and don't stare at all the details, but the gist of the plot is that we use what you just saw, but we also read out the light in a few other places. All of these yellow things are photodetectors. And then we take those signals, and to keep the light resonating in the whole interferometer, we feed them back through some digital filters, and we actuate on the mirrors. And we use 2 quadratures from each RF detector, and out of those we find 4 signals which we can use to actuate the 4 interferometer cavity lengths. This is just sort of some foreshadowing, but it's kind of key to see that our gravitational wave signal gets read out of this port, where almost all of the carrier and sideband light is destructively interfering. So there's almost no light here. So one of the main projects for this year has been getting the power in the interferometer built up. There's been a few hurdles to cross here. The lasers that we've got have been dying over, or have been degrading over the 3 or 4 years that we've had them on. They started out at about 10 or 11 watts, and as time has gone on, they've kind of gone down to 3 or 2 watts, and which had been okay in the past, where we were running the interferometers with only about half a watt or 1 watt. Recently, when we tried to turn up the power, we noticed, there's no power. And so we've had to go in and tune up these lasers. And that's been a lot of work, but we're now getting there. We're getting the lasers back up to where we want them. The second point there, we previously couldn't handle the high power. This is the reason why we were running at low power, is that in the beginning days, when we tried to just put the full power of the laser into the interferometer and run, we found there were several, not so much problems, but things had been overlooked. And the detectors would saturate. A lot of the detectors would see stray and scattered light. And then what we didn't realize until recently was that a lot of the mirrors were getting twisted around by the high powers, which gave too much radiation pressure and would misalign the interferometer. So we had been running with low power. Recently we upgraded the at the end of the last science run, the Hanford 4K laser was upgraded. It started out at 5 watts coming out of the laser instead of the 10 that had been designed. And we had, during the last science run, we'd been running with about 2 watts coming out of the input optics and about 1.5 watt going into the interferometer. Now, after the upgrade, at the at the best of times, it runs with almost the design level, 7.5 out of 8 watts, and almost 5 out of a design level of 6 watts running into the interferometer. So detecting all the light. Part of the problem in detecting all of the light is the dynamics of the interferometer. Before it gets into this state where all the light is resonating, like I show here, most of these mirrors are just sort of swinging around, and there's a lot of states in which, instead of getting a destructive interference here, you get some motion of the beam splitter or some motion of a cavity mirror, and you get constructive interference in this direction. And in that case, you can get as much as about half a joule coming out of this port, and it's enough to destroy the photodetectors we've got. So instead now, we use a different scheme where before the interferometer is running, we run on one photodetector, the one in the 4+1, that detects only 1% of the light. And then after we get running and the power is under control, we fade digitally over to 4 detectors which detect 99% of the light. And there's a fast plastic shutter which protects the 4 sensitive detectors. Radiation pressure. There's another thing that people have talked about is as far as a noise source in the gravitational wave band, but it hadn't been talked about in the DC sense for LIGO 1. We get about 5 to 15 kilowatts in the arm cavities now, and as the power is turned up, if the beam is a little bit off center, you can get a significant torquing. And over the 4K baseline, if you get, for instance, about 1 microradian of tilt on this end mirror, on these end mirrors, it's enough to give you almost no destructive interference out of here, and which increases the loss in this cavity and drops the power level by a factor of 2 or so. So the problem with that is it can lead to instabilities. You have this 10 kilowatts or so resonating around and giving you a torque, let's say on your end mirror, and then as it tilts from this torque, it dumps all of this power out of the dark port, reducing the power in the whole interferometer, and then the mirrors tilt back, the power builds up, and kind of goes back and forth. So to compensate this effect, there's been software installed which detects the power level in the interferometer and also tries to calculate the sort of the misalignment state of the 2 arms, and trying to calculate the amount of power which is being dumped out of the antisymmetric port. And this lets you calculate how much of a compensating force you need to apply to the mirrors to account for the fact that you have this instability due to power level fluctuations.
So do you have a full feedback loop controlling that instability?
No. So the software is installed. But
You will.
yeah, well, we'd like to, yeah. So we see the effect, and the software is there, but I think we have never. We're not sure how to run it yet. It's really the thing. We asked for the software. It was installed. We know it. It's what we asked for, but we haven't gotten it to work yet. That's like the answer.
The instability of these powers must be fairly weak. It's not a very strong signal.
Right. It's nothing that you can't overcome with the feedback.
Yeah.
But, well, so the effect is kind of like the pendulum frequency is sort of 3/4 of a hertz now. And what we see is that this seems to shift it down by some few tenths of a hertz. And we've shaped the servo loops in a way such that they have a lot of gain at the frequencies where there's most of the angular fluctuation. And as soon as this effect comes in, all of a sudden the sort of the stiffness of the interferometer changes. We no longer have gain at the right place. We have gain in a place where we don't need it, and no gain where we need it. The main thing I want to tell you about in the next few slides is a problem we have of not enough thermal lensing. So this is the same picture of the interferometer I showed before. There's a few input fields that come in, and the signal at the antisymmetric port where we get our gravitational wave signal is made from the beat between these fields at this port. The strain signal is generated by these frequency sidebands, which come out here and sit at this port. And when a gravitational wave comes through, it differentially shifts the phase in the two arms, letting a little bit of carrier light come out and produce a signal. So I say it's proportional to the field amplitude of the sideband in the TEM00 mode, beating against the carrier field, which is in the 00 mode. However, if for some reason you've done something here in this cavity which distorts the mode of the sideband, then what you can get is one of these fields not overlapping with the other. And so that's a plot I'm trying to show here, is that the field shape of the carrier coming out of the arm cavities is this. It's a bad choice of colors, but it's this blue Gaussian. And if you distort the cavity in here, then the sideband field can have this type of distortion. This is just an example distortion. This is not to say this is exactly what it looks like, but the idea basically is that you get the greatest signal, gravitational wave signal gain if the two fields that you're using to read it out have the same profile. And the other point to that is that one of the limiting noise sources that we have from sort of 100 hertz up to high frequencies shot noise is not dependent on the overlap of the fields. It only depends on the relative power in the carrier and the sideband. So this last plot was just sort of a guess of what kind of a distortion you could get. This is showing a measurement made of the profile of the carrier field and also of the carrier power and also the sideband power. So before you look at the numbers, you can see, yeah, they're not the same size, and in fact, not even the center of the beams don't even overlap. And this is basically because the initial design of the interferometers assumed that well, it assumed that you would be operating the interferometer at a certain power level, and it assumed that you knew the absorption in the mirrors, and that as you got to the design power levels, you would heat up the mirrors and induce a lens in the substrate of the glass through the effect of the dn dt, that there's a change in the index of refraction with temperature. Which, the idea is good, but the problems are that, well, all the mirrors seem to have a slightly different absorption, so you don't really get that kind of a thermal lens, and we're not operating at that power. And so you don't get the compensation that you hope for. You don't get a lens which would make this kind of a beam have this kind of shape. So this is a problem. I say there's a a 6% coupling. So this field which you're sending to the anti-symmetric port, you only really get, or we were only getting about 6% of it. And so that directly translates to a hit to our gravity wave sensitivity. So the solution so far has been to induce the right lens into the mirrors. So we put a CO2 laser, which operates at 10 microns, is a sort of the wavelength of heat, and is absorbed fully in fused silica. And we have one sitting, 2 per interferometer outside of the vacuum. We shoot them in through viewports, shape them correctly to either heat the center of the mass when we want to induce a focusing lens, or heat mainly the outsides of the mass by putting this kind of a mask in if we want to make a concave lens. So this is a series of plots of that, of one of the initial experiments of that. The beam without any lensing, the input beam to the interferometer, has sort of this kind of a size. And when we first lock the interferometer and look at the sideband shape, it's what you see on the top left with no heating. It's very big. As we start applying heat to the mirrors of the power recycling cavity, it slowly and slowly gets smaller and smaller until around 100 milliwatts it starts to overlap with the shape of the input beam. And then you can see with too much heat the beam gets too small. So the last thing that we did in Washington is maybe the most exciting thing, is that there was a reduction of this year of several noise sources which dominated the instrument. So this is not a Washington noise curve, but Louisiana. This is what I happen to have, and I'm more familiar with this one. This is the kind of thing we do in order to understand what the noise is. The black curve that you see is the measured displacement noise of the interferometer. The black dashed one is the design goal we're going for. And then all of the other colorful traces on here are all of the other noise sources we could think of, which were within sort of 2 orders of magnitude of the measured noise. And the process is, you make one of these plots, you identify all of the noise sources you can, which you have a handle on, and then you go around and start reducing them one by one, and seeing if the interferometer noise actually goes down. So this was the best budget we had of the noise in Louisiana during the last science run. Let me say a little bit more about this. Now, there's a lot of traces here, but there's sort of a general theme that all of the curves which you see over here coming down in the sort of the nominal noise, this wall here is dominated by seismic noise, which is this brown jagged trace here. But in fact, most of the interferometers have noise in excess of this, and there's a lot of these things with a steep slope coming down. All of the ones that you see on this plot are really they're self-inflicted noise sources. They come from trying to control all of the other degrees of freedom of the interferometer, which are not which we don't sense the gravitational wave in. So some of them control the pointing of the mirrors. Some of them control the position of the beam splitter or the recycling mirror. And then some of them are just noise in the electronics that we have. But that's all of the stuff in the low frequencies. All of the noise sources which dominate from 100 hertz up are some kind of sensing noise. So there's some sort of noise which is in the light or in the detection, or noise which is in the light or the detectors. So what we decided to do to get rid of these is we went at 4 fronts at the same time. For the auxiliary length loops, that control the short Michelson or the power recycling cavity. We did a thing which is sort of different from what our strategy had been in the past. The noise from those loops is the two curves to look at are this blue one, which come down here and have the shape from a filter we put in, and this purple one here. And you can see what we've done here to try and cut it out of our sensitive band is put in some kind of filter, which chops off the noise above 50 or 60 hertz. It worked okay for this run, but I mean, you can see it's at all frequencies below about 80 hertz. It would have been too big for us to ever get to our design sensitivity. So we tried different things. Instead of chopping off the gain by putting in filters, we decided to increase the gain, which is a little non-intuitive. And we decided to try to reduce the noise inherent in those loops themselves. Let's see. Do you have the time? Oh, okay, fine. So this is the same kind of noise plot that I just showed you for the interferometer noise, but these, should use a diagram. These are for these short degrees of freedom of the power recycled Michelson interferometer. So the one on the left, this is the differential motion, or motion of the beam splitter. And we tried to also budget for this noise to see, well, is the noise coming out of this degree of freedom what we expect, or is it in excess? And we put up a few sources we could think of, and there was something like a factor of 100 too much noise over most of the band. And we had no explanation for this. And you can see for the other short degree of freedom, it's about the same. From 20 hertz up to 80 hertz or so, there was some excess noise, and this was the reason why this was such a problem for the main differential strain sensing degree of freedom. Is that the coupling of these degrees of freedom to the dark part of the interferometer is small, but when the noise is sort of 100 or 1,000 times in excess of what you expect, it can matter. So why would the noise be so bad? After reducing the noise, we came up with an idea for. After we got rid of it, we came up with an explanation for why it was there. And the signal that you get at any of these detectors comes from, usually it's proportional to some length, some mirror motion. You can also get it. That's sort of the first order sensitivity that you get. There's a second order term which comes about from a gain modulation. So if you have a signal, if your mirrors are moving around, and you have a signal, let's say at 1 hertz, and then you also modulate the gain at 1 hertz, you can get then a bilinear product at 2 hertz. You can think about it in terms of this picture, I guess. If you say that the gain in your readout is the slope of this stick, then if this is the 0 point and then the gain is moving around, it's okay, you don't get a signal. But if you're actually moving out here, like it would be in the real world, that the mirrors are really moving around, then as you modulate the gain, you're going to get a fake signal, which is not real mirror motion, but just modulation of the gain in your readout. And so that was what was going on, was that we just, we had so much ground noise and so much mirror motion that the power levels in the interferometer were getting modulated and producing up conversion. So you look here, it's on a log scale, so it's a little hard to see, but this large pile of noise here at around 12 hertz is repeated at 24 and 36 and 48 with some broad noise around it. So this plot shows one of these degrees of freedom, the small Michelson degrees of freedom, and the difference between the blue and the red curve chiefly is that the gain below 20 hertz was increased by about a factor of 10. But you can see, even in this region from 20 hertz up to 100 hertz or so, where the gain wasn't increased, the signal is still reduced. And so the excess that we saw in these other degrees of freedom this whole time wasn't any kind of real noise from these degrees of freedom, but was just extra signal generated by nonlinearity in the readout. We had a couple more things we did. In the plot back here, let's see. There's a lot of traces here. You can see there's a green one here. I don't know. I mean, I stare at this a lot, so okay. And there's a pink one, which also comes along here. Those two come. Those are up here. I call them optical lever damping and wavefront sensor. These are the angular control servos that we have. So to keep the interferometer aligned, we read out the angles using various photodetectors and lasers, and then we try to feed back and keep the interferometer aligned. So they're really good angular sensors below 10 hertz, but above 10 hertz, where we're trying to detect gravity waves, they're full of noise, and so we try to aggressively filter them out or something. And so, yeah, they have a very steep shape over here. We've put in some kind of filtering, and they go down by 3 or 4 orders of magnitude here. But you know, they're not negligible. They're noisier than we'd like. So what we did to get rid of it is, after locking the interferometer, we put in more angular noise. We dithered, let's say, one optic at a fixed frequency, and we looked for the readout of that. We looked for that signal at the antisymmetric port in our gravity wave readout. And so if we excited at, say, 40 hertz, we look at the readout at 40 hertz, and then we go back and put in an equal signal into the interferometer length drive at that frequency to exactly cancel out the fake signal, which is brought in by the angular drive. Let me draw that. I don't think I said that so clear. If you imagine this is the optic, it's a little bit bigger than the real thing. We drive it by having these magnets glued on the back, and then some coils back here which we drive currents through. Then there's some more interferometer stuff out here, but basically the beam comes in and it hits the optic somewhere slightly off center. Nominally, if there's no angular noise, the readout for the interferometer works by sensing the phase shift of the light, which is reflected from here as the mirror moves back and forth. But even if you don't have any gravity waves, of course, you can, if you tilt this mirror, you can get a sort of an effective phase shift on the light, which just comes from the fact that there's a lever arm between here and the place where the beam hits. So you can never really perfectly tune this out. You'll never have the beams perfectly centered. But what you can do is, when you induce this noise by putting in an angular signal, if you measure it somewhere out here, you can feed this back and put a signal into the coils and put in exactly in sort of equal and opposite length drive, and totally cancel out the influence of angular noise. So that's what we did. Another problem we had was saturation in the electronics. Yeah, I said, yeah, we put in these 3 fields into the interferometer and then read them out. Well, at the dark port where we're trying to make our detection, usually, unfortunately, there are no gravity waves, and so there's actually almost no carrier light coming out of here. And so this little red line and the little blue line you see, it's mostly blue. And that's what this diagram is trying to show. That although you inject a large signal at the carrier frequency, the main laser beam wavelength, it's almost totally extinguished by the fact that you adjust the interferometer length to have destructive interference at this port. And so the main signal that you get is dominated by the beat between these 2 fields and not these 2. So rather than get a signal at the sort of chopping frequency or the phase modulation frequency, you get a signal at 2F, which normally is okay because you only look for signals at 1F. But this signal is in fact so large it saturates the electronics you have right on the front end before you can read it out. And this picture is a schematic of how the actual detection is done. This is one of the. All right. Well, okay. So the picture here, this is one of our best photodiodes. It has one of the lowest noises and happens to scatter the least amount of light, so I like to show it off. We installed it. It's a nice story. I found this one in a bag in an optics lab about 3 days before the S2 science run, for which papers are maybe soon going to come out. And there it was, and it had never been used. I took it out, and it sort of looked okay. And I knew that the ones that we had in service at the time were not so good. So sort of in the middle of the night, I went out there and stuck this guy in, and that's why Livingston was more sensitive than Hanford for that run, because of this detector and the fact that it had been ignored and left in a bag for who knows how long. Anyway, so how does the detector work? This is the active element, this little dark patch right in the middle. The beam comes in from this side, hits a mirror which you can't see but is mounted on this black thing, and then hits the diode. And anything which is scattered from there goes into this little beam dump here. And then the signal travels out of this little cable here and eventually gets digitized. But what goes on inside of here? This is it's not a real schematic, but it's to give you a feel for how it works. You can model the photodiode as a capacitor and a resistor with a current source in parallel to it. And since we're modulating at a frequency of about 25 megahertz, and sort of CB frequencies, to amplify the signal, we put a tuned inductor in series with it, and the arrows to show that it's adjustable. And so this forms a resonant circuit at the resonance frequency of this LC circuit. And so it resonantly builds up the signal which is at the 1F modulation frequency. But of course we have this problem from the 2F beat. And so we also put in another resonator, but this time a notch, which is formed by this inductor and this capacitor here. The saturation problem that we have is actually in this amplifier, which then sends a signal sort of down this cable here and to where we digitize it. And so we were kind of at a loss of what to do. We put in this notch, and still, the electronics were saturating. And we didn't have any good ideas besides lower the power or something like that. So one idea, which surprisingly worked, is to put a notch in the feedback of this amplifier, which I would have guessed would have been unstable. But So normally, this is the non-inverting input and the inverting input of the amplifier. And normally it's just a plain resistive feedback. Ignore the C and the L. And the ratio of the sum of these two resistors to this guy gives you the gain of this amplifier. And so typically we run this thing with a gain of about 10. And so it amplifies not only the 1F signal, but also the 2F signal by a factor of 10. So we put in this notch here. So we tune this thing to be at 2F. And that effectively makes this a short. And so this amplifier no longer has a gain of 10 at 2F. And so it has a gain of 1 instead. So it reduces the 2F signal by about a factor of 10. And people with sharp eyes will notice that there's nothing on here which says photodetector saturation. And this is because this is December of '03, and we just didn't know back then. This is a sort of in the field innovation around August. And it worked, which is important. The last noise source I want to talk about is this mystery noise source we've had in the interferometers for, I think, since maybe January of 2003, so almost 2 years. This high frequency part, which when people talk about the purple curve, our design curve, they'll say we're limited by shot noise up here. But we've seen that, well, yeah, it's true, but for some reason there's this bump. And what's that all about? Well, we turned up the power, we turned down the power, we found that the bump doesn't really change, it stays at the same place. And it's been there for a while. And at first it was only in the Livingston interferometer because the other ones weren't sensitive enough. Later we saw it in both of the 4K interferometers, but for some reason not in the 2K interferometer. And it's still not understood. But what it turned out to be was another unexpected noise source. It turned out to be phase noise on the oscillator which we use to generate the modulation sidebands. So it was decided long ago that we could get a pretty low noise RF oscillator, a Marconi oscillator, and use that to generate the sidebands. And it wouldn't matter. It wouldn't enter into our. It wouldn't affect the interferometer sensitivity. And normally that's true. If you have some sort of phase jitter on the basically the clock which is generating the sideband, it's okay. As your frequency wanders around, you're demodulating with the same jittering thing, and so there's some sort of common mode rejection. So you don't really care if over the course of a day the thing goes 25 megahertz plus 1 hertz or minus 1 hertz or something. They're still both locked to each other, and so in some sense it doesn't matter. But if that's true as long as they really do subtract. But what I don't show here is between where this kind of thing happens and where the beam gets into the interferometer, there's some conditioning optics here, some cavities. And those cavities have a line width of about a few kilohertz. And so, let's see. So a cavity that has, let's say, a transmission function like this, where this is power and this is frequency, will have a phase shift as you go through the resonance, something like this. And so you'll get between this point where you're on resonance in these input cavities, and when you fall off way out here, you'll have a 90-degree phase shift for a field transmitted through there. And so we operate generally on resonance of our cavities, so we can get the light through. But one of the input cavities has a full width of about 8 kilohertz. And so there actually is some phase shift to the light which passes through. And so if you have noise on the the optical sidebands which you pass through, they'll get filtered out or somewhat suppressed as you go to higher and higher frequencies, whereas the noise which is on the cable which goes to your electronics doesn't get filtered out, it just goes along this cable. And so this gives rise to this, well, we think this gives rise to this coupling that we see. And so if you actually look at the phase noise coming out of these Marconi signal generators, they have a bump, which is pretty much of the shape that we saw in the interferometer noise. So what we did was by, I mean, I say low noise here. That's what the company says, and I think at the time that was considered low noise, and so the number it's about 3 times 10 to the minus 7 radians per root hertz, I think kilohertz. It seemed low noise. It was lower noise than anything else you could buy that had a knob on it that you could tune the frequency. But if you do a Google search for low phase noise, you get a company called Wenzel, which makes an ultra low phase noise oscillator, which is it's less, and it's about 30 times less phase noise. And so, the beauty of Google, I ordered one of these because, really I ordered one because somebody told me that part of somewhere in my thesis had to be something about this oscillator phase noise. And this is before we knew what this was. And I didn't have a way to measure it, so we had to get something which was quieter than what we had. So I bought this thing, and the idea was to go down there and measure it at some point so I could put a plot into my thesis. That was the whole motivation. It cost a few $100. We went down there and measured it, and sure enough, there it was. It was actually a real noise source, and not just a make-work project.
So there was a real reason to let you finish your thesis.
Well, each of these sections, no, I don't know about that. Most of those sections were not so useful. In any case, so we were able to explain this sort of high-frequency bump, this is in the Hanford 4K, by the phase noise. And I'll show you a plot later of what happened when we put the crystal in. Another effect, which is an active study of our modeling group here, is that doing this active thermal lensing that I was talking about also seems to reduce the coupling of this phase noise into the interferometer output. And what that means is rather than put in, let's see, so the nominal way we do the lensing is a CO2 laser comes in and heats this optic and this optic, and basically forms a lens in the bulk, in the glass. And so as the light travels around, it gets slightly focused and is stable. It just keeps bouncing back and forth. What we did to lower the phase noise coupling was differential, which is to say, rather than put the same amount of heat into both, we put some heat into one and actually lowered the heat level into the other. And, well, it's not understood, but so it also seems to reduce the phase noise coupling. So yeah, we had these 4 things. The first 3 here are especially, they're not really new things. They had been done one at a time, and there had been no difference in the interferometer noise. And it's because they were of about the same level. And you would, you'd do one or you'd do 2 of them, and you'd see no change in the interferometer noise and say, well, that wasn't such a good idea, so we'll revert that one. And you try the 3rd one, and of course no change. And you do, various permutations of them, but until we did all 3 at the same time, there was no effect. And so then this was the result, the red curve on somewhere mid-August, doing all of these things at the same time, putting in the crystal and doing the differential heating, drop the oscillator phase noise by a pretty good level to where it's over this, almost the whole band dominated by real shot noise.
This is Hanford.
4K a while ago, and then pretty much over the whole band, it's getting very close to where the interferometer was designed to be. And needless to say, we were very happy to see this. We were also we were a little bit surprised because, like I said, we did all of the things separately and didn't see this kind of improvement. But it stood up and seems to still have this kind of sensitivity. And it's really close. I just want to point that out again. I mean, this is really, it's almost like nothing.
Totally arbitrary.
It is. You know, it's this purple curve was made something like more than 10 years ago. So the fact that there's even any relation, I think, is pretty amazing. So this is like the plot I showed before, but with some more knowledge. The old plot was 9 months before, and so this one has a lot more noise sources that we think we understand better. This lower region is still full of the same stuff as before. It's self-inflicted noises from our control systems. Even this blue and red stuff up here. The yellow curve, which goes all the way up here, is shot noise and some noise from the photodetectors. The dark green curve here, this is a little bit out of date, but this is noise from the output electronics we have, which drive the suspensions around. I mean, maybe, so it's really enticing. If you look in this little gap here, you go, well, there's this dark green curve. Sorry, and the light green one is the quadrature sum of all of the sources we know of, and it pretty well explains the black curve here, which is the measured noise we have. And so, you know, wow. That's so neat.
Look at the way to
This is another thing. We do have a lot of problems from this at the sites. The loose cables give us, for high frequency connections, give us a lot of, well, they don't give color changes, but anyway, getting back here. You look at this and you go, well, there's only one noise source here. So if I get rid of this dark green one, we'll actually do better than our design sensitivity in this little gap. And you know, pay raises for all. But so sadly, we did knock that down by about a factor of 5, and the interferometer noise didn't change. So that's how much weight you should put in this. But no, I don't want to denigrate this. There's a really good grad student at Hanford right now. He's been there for a couple of years, and this is his noise curve, which I carry around and show. And he's about to graduate in sort of 6 months or so. So this is an advertisement. He's done a really good job. And so near-term plans, what are we going to do next? And skip that stuff. For Livingston, for the Louisiana interferometer, we want to do this thermal lensing. We want to increase the laser power, and we want to copy all of the noise improvements we can that were done on the Hanford 4K. On the good one there, the Hanford 4K, we want to increase the duty cycle to beyond this 65% that it seems to have had all this time. We also want to get more stable angular control so that the noise is very steady and that there's no change, and we sit at our maximum sensitivity for the entire run. And then this other point here is we want to have some limited seismic isolation to reduce the ground noise at about 1/10 of a hertz that you get from ocean waves or so. And a Hanford 2K, which is really neglected, I think we want to do all of these things. So, yeah, I mean, I say copy noise improvements. You say, well, yeah, that's easier said than done, right? How would you can't, you can't do it with your mouse or something. It's real hardware changes. But I had an idea. Could do this. And so we we looked back here. There was this guy who'd done this stuff. And so we got him a plane ticket. And we sent him to Livingston. And, you know, sure enough, hasn't fixed everything yet, but, you know, there's a factor of 3 or 4 improvement on top of the last science run. And the red curve, now the Livingston noise is, you know, almost neck and neck with the Washington interferometer. And there actually there's a later curve where this end has been flattened out by the same trick, putting in a low noise crystal oscillator. So it's looking real good. There's just only, you know, this factor of a few between them, and we know pretty much what we have to do in these bands here. There's a lot of you know, there's some busted electronics which we're going to fix next in the next week. So yeah, I say we're also going to do these other 2 things. Just tomorrow and the next day, we'll increase the laser power into the interferometer by a factor of 4. And 3 out of 4, we've copied over the photodetector notching, the angular noise reduction, and the reduction of the auxiliary length loop stuff. So the last thing left to do is just this thing here, which seemed to have worked for 1 day so far. So there's good indications that that'll work also, and hopefully we'll match or exceed the sensitivity of the Hanford machine. So my last slide. Because of the seismic isolation upgrade, all of the interferometers can run all day and all night. All of the servos are on, so all angles, all positions of all beams are under control for the interferometer. And so it's really a pleasure when you go to work on it now. You turn it on, and, you know, as long as no one has touched it, it's exactly the same as it was the day before. And, you know, rain or shine, storm, no storm, you know, people working, it's exactly the same. And that's how you want it. And the sensitivity is really close. And, you know, for you know, several people in this room have been working on it for, I don't know how many years.